All right, thank you so much. It's a pleasure to be here. I'm Jean-Gabriel Young, so I'm at the University of Vermont in the Department of Mathematics and Statistics, but I swear to God, my PhD is in physics, so it's very good to be back home for at least the time of the week. And so at the University of Vermont, we do many things. I'm also in the Complex Systems Center, where we study these kinds of dynamics, and the Translational Infectious Disease Center, which is a really interesting place that mixes the insights. We have like doctors, immunologists, and modelers like myself. So it's a very happy and interesting mix where we have to learn to talk to each other to solve problems with models and with biology. And this is what I want to talk to you about today. So in the past few years in the lab, we've been gathering these kinds of data about networked process from various places. I work, for example, with the hospital right across the hall at the University of Vermont, where in the past 10 years, we have now very detailed electronic records of what people do when they're in the hospital. So we know where people go, what doctors do they see, what drugs they get. And so it's a very kind of natural setting to study contagion process on networks at the level of individuals. It's the kind of data we've never had before. And there's various other places we collaborate with that have data of the same kind. So there's a beautiful experiment ran out of UMass and the Broad Institute called Operation Outbreak, where they put a little kind of fake simulation of disease on your phone, and if you're near someone with Bluetooth, the disease can pass between two people. And they run these simulations in various universities across the world, and you also have a very kind of detailed dynamical process on networks where we have all the data. We know where people are, who's active with a disease, and so on. And during the pandemic, we've all encountered this, where the health authorities would call you up and follow the disease, for example, COVID with contact tracing. Okay, so the point I want to make is that we're in an era of unprecedented data for dynamical processes on networks, so we can start mixing the models we've been doing for 25 years now in network science with actual data and kind of see, do they match? Where are the disparities? Kind of how can we improve our models and how we can talk about the real world with these kinds of interesting physics model. And so the network vision really for this kind of approach to network science is to have data on one side, kind of dynamical states, for example. We might know who's currently infected with the disease or so on. Mobility, where people are. Maybe we ask surveys, what have people done? Maybe we have digital traces, like presence on Twitter and so on. And then there's a network in the loop, right? So that's what we have all in our models. There's a network of contacts between individuals and a dynamic on it. Okay? And somehow we would like to bridge the data with the network to gather some insights about, so in the context of epidemiology, maybe we want to forecast, say, what's going to happen. Maybe we want to test interventions, so we have a nice mechanistic model, we can do that. Or maybe we want to understand something about the parameters, right? Is the disease really virulent or not? And so once you start facing the complexity of all of this, you can build these like very complex edifice of mathematics and machine learning and get caught into the like intricacies of this. And that can be frustrating sometimes. You want to step back and you have like this whole pyramid, it's now skewed, it doesn't really work. And so I really want to go back to simple models and understand what can simple models actually tell us about this kind of setting. And so I will start really simply with a model for generic contagion. So we have a network. Nodes have states. Okay, so let's say the simple thing where people are susceptible, infectious, and maybe recovered, or maybe they become susceptible again. I will denote this with colors. So we have, for example, the dark gray would be recovered, and orange would be infectious. Okay? And maybe we recover with constant probability, so it's a discrete time dynamics where people go from being infectious to recovered with some probability. And the interesting thing that will make a bit different from all the simple models we've been doing for a long time is that we'll say the infection probability basically depends upon how many infectious contacts you have. So for example, here node A has 2 infectious contacts, right? There's 2 orange nodes in its neighborhood. So we would say like the infection probability of the node in the middle would be a function that depends on 2. And there would be a different function for node B because it has a single infectious contact. Okay, so just a simple setup like this. And with this simple setup, you can express quite a lot of very well-known infectious model, right? So if, for example, all infections are independent, so for every edge that exists, I infect the node with a probability beta. Okay? So that's just coin flips. And so therefore, in this setup, the probability that, for example, node A would be infected is 1 minus beta to the nu. So it's the probability, right, that none of the neighbors infect the node, and the complement on that gives you the probability that the node gets infected, right? And so that gives you these kinds of infection function, as when you increase the number of neighbors, you have this kind of saturation effect. And that's the classical kind of simple infection probability. Or if you do Huberman math, you just multiply. Okay. That's a test of how much online you guys are. So nobody is on Twitter. That's good. Saves your sanity. Okay, so it's not that. It's the first. But you can express more interesting function this way. So there's this classical threshold model, for example, Watts in 2002 introduced this, that basically says, okay, you need a minimum number of infectious neighbors to become infectious yourself. So there's a threshold function, and then there's an infection probability beta once you cross that threshold. And so these functions look like this, and so maybe you need like at least 2 of your neighbors to become infected with some probability. And that's what people call complex contagions, right? And the goal here is to model things such as if you want to go see a movie, like maybe your friend that always goes to the movies and loves everything is not going to convince you, but once 2 people tell you about a movie, then maybe now that's interesting and you're going to go, right? So there's kinds of these complex dynamics that you can express with this. Okay, and of course, when you start having these functions, you can like write arbitrary models, maybe even decreasing effect. It's a very kind of free generate contagion model. Okay, so that's on network. If you want to do a bit of analysis of these things, you can simplify things and use the good old compartments, right? So still same idea. Nodes have various states. They transition between states. But instead of tracking the states of every node, we'll track just a density in these little boxes, so the kind of fraction of people that are infected, fraction of people that are susceptible, and so on. Now we're going to be kind of everything continuous, so the transitions are going to be in terms of rates and not probabilities. And you can kind of get to the same idea of a dependency upon the neighborhood by parameterizing this infection rate by the density of individuals. Okay? And the system then becomes tracked by these classical ODEs, where, for example, the change in the density of susceptible individuals is given by the rate of contacts between them, I times S, and then there's this infection rate beta, which, different from normal kind of models, will make a function of I. Okay, but before I go into solving these kinds of models, I just want to make the point that this is directly analogous, the fact that we have a function, beta, instead of having a constant, to these functions for the discrete case. Okay? So in the classical models, SIS, SIR, we have the function beta be a constant, right? So the rate at which people become infected doesn't depend on the state of the system. But you can, again, make some kind of notions of social reinforcement. Right? So if the rate of infection increases with the density, that would be the equivalent of like, now it's not one of your friends tells you about a movie and 2 of your friends tell you about a movie and then you go. It's more like the more you see chatter about a movie on the internet, then maybe you go and there's this kind of constant increase. Okay, so it's directly analogous. Okay, and so why am I posing these models? Why am I stating that they would be interesting to study, even if they seem kind of dumb and simple? It's that they turn out to be very effective and like very flexible effective models. So we're not claiming the world looks like that, but they can express so many things that they turn out to be interesting to study for 2 reasons. So the first reason is that they're like literal description of simple mechanisms. So there are some contagion processes that work like this for real. So you might have seen the independent cascade. That's a very old paper, 2003, at the beginning of network science and the internet, where people were trying to understand how might I influence like various people on a social network to spread information as efficiently as I can. And they were using this independent cascade. Basically, everyone passes the information with some probability to their neighbors. That's a special case of these models. Percolation, SIR, threshold contagions are all special cases, as I've shown. Maybe more interestingly, they can kind of behave exactly like very complex mechanisms. So they're kind of like a universality class in the sense that like I can write very intricate mechanistic model, and basically they will behave the same as these simpler models. I'll go into more details, but that could be dose responses, for example. So that's a model in which you imagine kind of talking with someone and giving them, during COVID, so maybe you give them a bit of COVID because you had a physical interaction, and then somebody else talks to them, gives them a bit of a dose, and it kind of builds up, and at some point they become sick. So these dose responses can be mapped exactly, and I'll talk about it a little bit later. And there's kind of also various behavioral reasons where you can get to these, or an interesting kind of recent PRL, of which this is one figure, shows that basically if you have a network where the contagions are very simple, so it's just like independent coin flip, like in the classical story, but that the probability of getting infected gets modulated by the environment. So maybe some environments are really like good for spread, like a bar, some are not, like an hospital. So if you have this mixture of environments, you can end up having complex contagion in effect. So we're building a list in the lab, and it keeps growing, of models that behave like these simple models. And so, okay, I want to like make this point a little bit more clear, that you can get complex or weird contagions from stacking simple assumptions. And so I'm going to talk for a bit about interacting contagion as one example. And so in the interacting contagion setup, you imagine having a network where you have two diseases that spread at the same time. Maybe, like RSV and COVID, or RSV and the flu, okay? And these two diseases, so I gave them two different colors, contagion 1 and contagion 2, and some people can have both at the same time. And the idea is that usually we assume they will help each other, right? So maybe like if you have both, you become way more susceptible to passing the disease, and so there's this synergy effect. And the insight is that actually, let's say like there's one disease you don't really know about. Maybe we're at the beginning of COVID, so we are just tracking the flu. The flu can look like it behaves in a complex manner because of that second disease. And the idea is that like once you have two diseases, maybe there's a node you don't know has a second disease, but there's this synergistic effect, right? So the more neighbors you have, the more likely you have to have neighbors that have the two disease, but you don't know, and therefore the infection probability kind of increases as a function of the number of neighbors. So that's the intuition. We can make this a bit more precise. So let's model this mathematically. So we'll do a simple compartment model. So we have two contagions. The network is fully mixed, so we can track everything with ODEs. There's two contagion states, so SIS. And then we track this with this little bracket operators that just basically tells me the density of nodes with state X and Y. And then we'll say the infection rate is beta, but if you have two diseases, you get beta plus alpha for your spreading. Okay? So the equations are a mouthful, but we can explain all of these terms. So let's go through them just so we are on the same page. And so here, for example, if I want to track the density of people with two diseases, right? So they're infected with the first and infected with the second. Okay, so let's do the easy one, the negative term first, right? So at which rate do we lose these double infections? Well, it's either you heal from the first disease or you heal from the second, right? So that's the rate of exiting that compartment. And then entering into that compartment, well, okay, how can you become doubly infected? It's either you were infected with the first disease and now you need to become infected with the second, right? So how many nodes have IS? And how do we become infected with the second disease? It's either from nodes that have the first, not the first, but only the second, so that's beta. And then this is the synergistic effect here, the alpha plus beta, right? So if you have the two, you spread very much more. And you get kind of symmetrical term here for the second disease. So that's the kind of evolution we can get from these. We can write equations of the same kind for density of nodes with infected with the first and not the second. And the upshot, I don't want to dwell too much on this, but once you have the two evolution, you can add them up and ask, what is the evolution of the number of nodes with a single disease, all right? So the first disease, and we kind of ignore the second, because remember, we're like modeling maybe the flu, we don't know about COVID right now, okay? And so we have how many nodes have the flu? Well, the change is going to be the number of nodes that have the flu and COVID, and just the flu, but not COVID, okay? And once you look at these two equations, you add the equations you do, and you can rework the equations to basically end up with something that looks like a complex contagion. You add these two ODEs, and the ODEs will look like the time evolution of an SIS with a complex function. And so from these two simple contagions, we created a complex contagion. That's the key point here. We have a single contagion that behaves in a complex way because of this latent disease. Okay, so when we wrote this paper, it kind of made the news, and we had like amazing headlines, and so I want to share some. So that was like, they were phrased as the interaction of disease and memes. And so people made these beautiful things and wrote kind of interesting headlines. Contagion disease spreads a lot like memes, which was not really, I mean, it is kind of the point, right? Because people have been using memes, complex contagion to model human behavior in memes. And so it was like a profound point that disease could behave like memes, in a sense. But of course, this got like commenters on the internet pretty happy. And they were like, you're wasting research money. Maybe vice versa. Talk about their research. It was in Nature Physics, so I would argue maybe yes, and so on. So that was a little fun. And maybe this is my favorite meme that came out of this era. It was at the beginning of COVID. So some people mixed viruses with cats. Yeah. Cool. Okay. Really quickly, I just want to point out a few other mappings. I'm not going to go into the mathematical details, but this is a beautiful paper by Dodds and Watts in PRL in 2004 that was also making a kind of the same point. So this dose response mechanism kind of can make contagion look complex. And here it's the idea I already talked about, that like you have some contacts, each of them infect you with some probability beta, and once they do, they give you like a little dose. And you build up your memory, and at some point, once it crosses a threshold, you become sick. And playing with the distribution of doses can kind of create any contagions you want. So you have this figure where they're showing, for example, you have threshold contagion. So that would be the case where you have a threshold, and not until you meet it do you become infected. So that becomes a function of the number of infectious neighbors you encounter, right? Every neighbors maybe give you 1 dose, and you need 5 doses, right? So that makes a model that behaves in a complex way. You can get the traditional classical behavior and kind of a lot of in between. And one of the cool points that they were making in this paper is that it was kind of allowing you to classify types of contagion also by the phase diagrams, they would say. They would create. So for example, we had this classical epidemic model case where when the contagion function has this diminishing return, we get these classical epidemic model with a second order phase transition. When the models are more kind of complex, when they have these threshold behavior or these sigmoid functions, we have these first order phase transition bifurcation diagram that kind of arise as a result. And so we map from the contagions function to kind of the bifurcation diagram. Lets us know that when we see these things, it's maybe the signature of something complex. Third example, prudent behavior. In this model, the idea is it's an infectious model, so it was used to model the effect of replacing people at work. So if you get sick, a nurse, for example, will go back home, and then you have a new nurse come in, and that nurse is healthy, but is in kind of in a hot spot in the room, right? The person that was sick for a reason. And so you put people in danger with this prudent behavior, and so that's also like a very complex mechanistic model. Now there's human behavior and economics in it, right, for a sense. And just from these simple assumptions, you also get these complex contagion signatures, where we have these discontinuities, or for example, this is a function, so the proportion of infection is a function of time, and you can see these super exponential speed up, where you go faster even than what you would get with the classical SIR dynamics. So it means that the infection function is nonlinear. Okay. And so at this point, I want to just take a moment to like say, okay, so we have all these functions, these complex mechanism, and all they do in a sense is just vary this infection function. So given number of neighbors or the density of state, how infectious is the disease, that kind of be explained all this way. And so one of the reasons that I'm now in the Department of Statistics is that I focus most on the inference problem. So we assume a model, and now we want to kind of learn or infer from observation what was the actual rules that generated it. So I'm less interested in solving these model forwards. They've essentially been all solved. So now I'm interested in taking the data and informing these models. So I want to talk about how we do this for these two models. So the first one is a paper with Samuel Scarpino at Northeastern and Laurent Bardufresne, who co-leads my lab at UVM with myself. And so we're talking about this simple model I defined earlier. So compartment model with the function, the infection function, beta I kind of being a rate. So it's we need to understand how do we even fit this rate from data. Okay? And so just to give you a little bit of a feeling for what we might get from this model. So if I hold everything constant, right? In this model, the only thing that vary are the rates, and that's it. That's the only parameters I can change. So for example, if the recovery rate is the same, and I have this infection function that starts very low and kind of peaks as soon as there's like a lot of infectious, we will get these very, very fast dynamics where you start the disease, then you get to everybody because we get at this plateau, so everything accelerates really fast, we saturate, and then we're done. But we can write very arbitrary functions and get different dynamics, right? So we can have, for example, in the middle, this probability starts really high, but then decays really quickly. So we will kind of hit a critical density, and then we plummet. Okay? And you can get really, really weird dynamics by just changing this beta. And so the question is, like, given these time series, can I say what is beta? But to make our life a little bit harder, and we'll assume kind of real-world setting where the data is noisy. So we don't actually get the nice, beautiful, smooth functions. We need to kind of add a bit of math. Okay, so what does that look like? If we want to set this up as an inference problem, we'll think of our time series in Python notation, y on the range 1 to t, right? So that's for example, the incidence of the disease or the prevalence of the disease at every time step, discrete observations. They might be non-homogeneous in the sense you might have like a couple one day, then nothing for a week, and then a couple at the end of the week, and so on. And what we want to learn is this infection function beta, and also recovery rate. And since we have a noise, we kind of need to also learn the noise model. And given these parameters, we assume that the ODE model is still true. Okay, so how do we set this up? Well, we assume that the data is modeled normal IID, centered on the true prevalence or incidence of the model. So what we mean by this is that we imagine integrating the ODE, and then we measure a value that's observed with some noise around normal. And then okay, you can use Bayes' formula to set this up as an inference problem. So what we really want is this posterior distribution, so a distribution over the value of the function, the rates, and the noise parameters, given the observations. And it turns out that like this used to be very long. It used to be that you needed to work for several weeks to write your samplers to kind of sample from this distribution, but in the future, or today, there's this beautiful program called STAN, where you can basically write your model, and it will generate samples from you with an algorithm called Hamiltonian Monte Carlo. So if you've not seen this before, Hamiltonian Monte Carlo is like a beautiful algorithm based on physics, where you imagine a particle kind of representing the function, representing the parameters. So every location in that space is like a value of beta, gamma, and sigma. and you move that particle around, and that gives you a sample from an arbitrary distribution, where the shape of that distribution is the log of the posterior. So it's kind of a potential, and you move around that potential at random. It's great. It works magically. It's super fast, and it takes like a day to implement. Okay, but the problem is a function is not something that you can store in a computer like really well, right? Like what's a curve, right? I could like give every point, but it's a continuous object. So the main insight of that paper was that we can actually parameterize these infection functions with something called B-splines. So it's Bernstein polynomials. Okay? And it's so Bernstein polynomials are functions that map anything between 0 and 1, so a density of infected, to a real number, a positive real number. And you achieve this by having like a sum over this kind of binomial basis. And the free parameter here to express the family of functions is n, so that's the degree, so how many kind of basis points you have, and also xi. So these parameters basically tells you the importance of each part of the basis. And for a different choice of xi, you get different functions. So you can kind of express all these functions I've been showing you as special cases. And if you're on Twitter, you've probably seen the CAN networks. So they're Kolmogorov networks, the new parameterization for MLPs. They use these B-splines to parameterize functions. So I guess what is old is new again. Okay, so the insight is we can replace this notion of what is a function by a set of coefficients. So that makes sampling easy. So really now what we're sampling is a set of coefficients for the basis, and an infection rate, and a kind of noise parameters that says how far we are from what we fit. And so that's what it looks like in practice. So here I have an incidence time series, so that's the kind of number of new cases I get in a day from COVID, for example. And here is what the sampling looks like. So each of these lines is a possible explanation that is fitted to the incidence curve. So the incidence curve, you can see the little green line is kind of goes through the points. And the sampler tells me that all of these are possible explanation that leads to a good time series. So in the figures I'm going to show from now on, basically what we did is we took all these lines and summarized them by an interval. So the interval is like 95% of samples at every given I. And then on top of that, we outlaid a few samples because the intervals don't capture lines being off balance, and then there's kind of a modal one. So this is the most likely, shown in black. Okay, and so that's what it's look in practice. So the first thing I do every time I start a new inference problem is I create synthetic data and I verify that it works to kind of understand what could go wrong. And so here we created fake data with this function in black, and then we basically started adding noise. So you can see that by the end, the points are really, really far from the real curve. And it kind of like robustly tells us what's the shape of this contagion. It's also robust to like not having a lot of data. So you can start with having loads and loads of measurements. Like in public health, we would never hope having that many measurements. And then you can tin it to maybe like 1 sample a week or something like that. And you still get a pretty good sense that, is this function flat or not flat, and so on. Which brings us back to this notion of interacting contagion. So here we did like a pretty fun experiments, which I recommend doing with your co-authors if you ever do an inference project. So Laurent generated time series without telling me how he did it. He just gave me 2 time series. And the way he did it was to take a network of little cliques like this, send 2 diseases on them, and then either have them basically like be independent, so they do whatever they want, or be cooperative. So I have like a synergy where when you have the 2 diseases, you spread faster. And then he gave me the time series of like one of the disease, and didn't label the file. It was like time series 1, time series 2. Good luck. Tell me which one has an interaction. Okay, so and if you plot them, they like look really similar, right? These are, as a function of time, the prevalence. From the eye, I couldn't really tell the difference. But once you put these algorithms to the test, That's what you get, the blue and the green curve. And so the blue curve is fitted to this independent case. And if you remember, right, independent case is the classical SIS model where you don't have any benefit from having any neighbors. So that should be modeled by what we call like the simple contagion, right? So a flat function. This is pretty good for me. It's like mostly flat. I would say the derivative is close to 0 everywhere-ish. And so we classify this as a simple contagion. And then in green, we have an increase, so that's complex. Yeah, Marcus? Yeah, so it's able to pick up like basically the different rate of accelerations, and that's enough to make a difference between the two. So it's quite remarkable, yeah. And, well, so I'm modeling everything with SIS with a unfixed function. Yeah, exactly. And then the question is, right, which one is complex, which one is simple? And that should be reflected in the function beta being flat or not flat. And it kind of turns out to be the case. Right here, it's like a crappy measure of nonlinearity. It's like the ratio of the maximum to the minimum. So it should be 1 if it's simple. It should be large if it's not simple-ish. And so we can kind of basically delineate the two functions. So that's a good test for me. And then last thing we did, we took it to the real world. So there's this interesting disease, if interesting is a word. So dengue, it's endemic in Puerto Rico. And one of the things about dengue is that it has multiple strains. So there's like 4 strains, different strains come different years. We might think, or at that point, we thought there might be interactions. So I've spoken with more doctors now at the Translational Infectious Disease Center. They don't think it's true. But nonetheless, we think maybe the disease interacts with something. Maybe it's a social phenomenon. There's many explanations. But once you take the empirical incidence or prevalence data, you can fit with the model, and you get this really interesting function that kind of starts up, increases, and tails at the end. And so there might be, we think now that it could be explained by behavior. Basically, people change their behavior late in the season, and that reduces the infection. As the infection density increases in the population, people become more careful, basically, and try to avoid mosquito-dense region and so on. Okay, and so that's it for this model. The key takeaways, I think, are that just with this simple beta function, we can model time series in a very flexible ways, and these B-splines are kind of an obscure mathematical thing, but they turn out to be really useful. There's opportunities we've not acted on, so if that's something of interest to you, come talk to me. For example, one thing we talked about was to do a zoo of dynamics, right? So I listed 4 examples of dynamics that could look complex, but really what I would want is kind of a Wikipedia page or like a paper that tells me like, this is complex, this is not complex, this is simple, right? And like kind of use it as a classification scheme for known dynamics. That would be really cool. And just a complexity index, right? We were working on running this on all time series of disease out there to kind of rank them by complexity. Okay, any question before I move? Yes, Thomas. Yeah. It's the intuition, the reason is that it's the only basis I know that maps 0, 1 to the positive reals, which is what we need for these contagion functions. They need to take as input a density of infected and output the rate, right? So if you know of other bases, like they're actually terrible to fit because they require a recursion formula to solve, so they're pretty slow. So anything that's better would be great. So I'm open to suggestions. Okay. How much time? Okay. So now I want to talk, this is a contagion on dynamics on networks workshop, and so far I've not had networks, right? It's like we had the mean field version with boxes. It's not very networky. So I want to talk about more kind of precision models that we do in the lab. This idea of estimating the functions, but from nodal states. So instead of now knowing like a fraction of people being infected, I want to talk about, specifically who's infected. And so this is work with Nicolas Naudry. who's a postdoc in the lab, now moving to UVA as an assistant professor, and Will Thompson, who's a PhD in the lab as well. And so for this, I'm going back to these simple models I started to talk with, right? So just to remember what's going on, we have a network. I'm going to write that A, the adjacency matrix, and we have a recovery rate, recovery probability, gamma. So at every step, nodes that are infected flip a coin with bias gamma and become susceptible again. And we have this infection with probability C nu that depends upon the number of infected neighbors. And what we're going to think about is kind of this notion of there's a true network out there that generates a time series. And the time series looks something like this, right? It's a matrix where every column is the state of every node at every time step. Okay? And so here in black, for example, the nodes would be infected. In white, they would be susceptible. And it's a steady state dynamics where they alternate between the two, SIS. Okay? And the goal is, given this time series, so I just show you the matrix, and I ask you, what is a network? What is the rules? What are the rules? Is it complex or is it simple that generated this? So quite kind of difficult inverse problem where there's not a lot of information to go with. But that's the kind of problems we're faced with day to day when we want to do precision medicine, right? That's what we know. We know who's sick, and that's basically it. Okay, so how do we set that up? I'm going to go into a bit more details here about the methods. So that's a state where we have the time series is a nodal state, so that's the matrix I showed you. We call it X. And then now the parameters that we need to solve for are this infection function, the recovery rate, the recovery probability, and the network structure. And the infection function, since it's a discrete system, will actually be parameterized as vector, right? So it's how likely are you to be infected if you have a single neighbor that's infected? How likely are you to be infected if you have two neighbors that are infected, and so on, all the way to n minus 1. So it's a long vector of probabilities. Okay, and once you have this model, what we're going to do is turn the crank on Bayes formalism, right? So we're going to say what's the probability of the parameters I want to infer given the observation x. So that's a product of a prior and a likelihood. And going into a bit more details of how we actually calculate this formula. So the likelihood is the kind of the crux here, and we want to assign a probability to the observations given the parameters. So what's the probability of this matrix X at the top given the adjacency matrix and the rates? And to give you a bit of intuition of how we actually compute this function, we can use like a number of assumptions to actually write it explicitly. It's not that difficult. So the first observation is that these dynamics are Markovian, right? So there's no memory in the system. So the state at time t plus 1 only depends upon the state at times t. So when you want to calculate the joint probability of all state, you can factor that out as a product over time steps, where the state at time t is a function of t minus 1 and nothing else. And these these transitions from time t minus 1 to time t are super simple. They're Bernoulli random variables. They're coin flips. So for example here, let's go through one of them, right? So when a square becomes from white to black, so when it is infected, that happens, right? So basically when it goes from susceptible to infected, that happens with the probability C nu. So the infection probability when you have nu I neighbor at time t minus 1. Or maybe an even simpler one, right? What's the probability that the black square becomes white? That's just the recovery probability. Okay, so gamma, right? So going from I back to S. And so if you have this time series, right, when you do the network, C and gamma, you can all calculate these things as a big product. And it turns out that if you kind of work out this product, it simplifies in a very nice form where there's a function that depends on the recovery rate. We're going to ignore it for now. And there's this product that only has two dependencies. It has the dependencies of the number of times a node with L infected neighbors was infected. So like you look at every time in the time series where someone had like 4 neighbors and became infected. So you call that M. And then you look in a time series, at every time where a node had 4 neighbors didn't become infected, you called that N. Okay. And those two numbers can be calculated. And it turns out that the likelihood is only a function of these two. And so once you have that, you take the product, and that gives you the likelihood. Questions? Okay. All right. And so that's kind of, this function is known. It's simple to compute. For the priors, we use kind of standard beta things. And once you have these two functions, basically you now have an estimator, right? So you have a function, a posterior distribution, where you can plug different assumptions. So you can say, like, is this my network? So you plug a certain explanation. Is this my contagion function? And it'll give you a probability. So you can treat this as a search problem, where you have a function that tells you which is the most likely network and contagion function at the same time. You can also treat this as a sampling problem. So essentially, right, this is a distribution. So if I somehow knew how to sample from this distribution, it would give me examples that are more or less likely. And so, for example, for my network, I could have 5 different samples that would be 5 different explanations of my matrix. So maybe some of these explanations would have an edge between 1 and 8. Some others wouldn't. And I would kind of have a probabilistic assessment of what's the structure. Yeah? No, exactly. There's way too many. It's like 2 to the n choose 2. So it's exponentially big. Yes. Exactly. So we're going to treat this as a sampling problem. So we're going to construct a sampler. It turns out to be a bit mathematically challenging. So I want to maybe make one little modification first. So the main technique, I mean, it's been introduced a number of times. It's mostly Tiago Peixoto has done lots of work on this. And the idea is that, okay, this is a distribution over networks, contagion functions, and probabilities. So that's kind of like too much at the same time. It's a big space, so we're going to kind of ignore part of the space. So we're going to use a technique of marginalization, where we're going to integrate over all contagion vectors and all probabilities of infection, and only keep a function in the network. So at least we're going to reduce the search space a little bit. And it turns out in Bayesian statistics, there's this thing called conjugate priors that make these integrals really easy. So if we assume that the probability, without seeing any data, of the contagion vectors is the product of beta functions, we get this nice product of beta function as the marginal. So these beta functions, right, if you've not seen them, they're a ratio of gamma functions. And so they can be computed numerically. It's not a big issue. And the point here is that we now have a probability of A given X, which is a product that's known. And we can use the Metropolis Hastings algorithm. There's various instantiation of the idea. Here's a naive one, where you start from a guess of what the network might be. So maybe you put no edge at all. And then you will just pick entries in the adjacency matrix and flip them. So like say, maybe there's an edge here. Let's try. And then you compute this probability, which is not hard to compute. You take the ratio, that gives you an acceptance probability, and then you flip with a probability. So it's like Glauber dynamics and for physicists. And it turns out that if you use these rules, okay, cool, I'm almost done. If you use these rules for evolving the network, then you will, in the long term, equilibrate on this distribution. And so that's what you get. Like you explore the space, you never actually go through every single network. You just walk around, get a bunch of networks that concentrate around the peak of the distribution. And so if that's your true network, this is what we infer. So we get a structure that's quite similar, just from sampling. I said naive because the flipping, like picking one entry at a time, is pretty slow. We are not guiding the search in any ways, right? We're just trying things at random. It's the maximally dumb thing to do. And so Tiago Peixoto has these 2 very nice papers that explain ways of doing this better. They have different models, but these ideas could be translated, I'm pretty sure, where you essentially flip, but smarter, instead of one at random. Okay, in the interest of time, I want to show you what we can learn with these tools. So that's one of the cool results. So if you have a true network and you simulate a complex contagion on this and a simple contagion, right? So is there a benefit? So the simple contagion is the classical thing where you have the diminishing return. A complex contagion here is a threshold. So you need at least 2 neighbors to become infected. You kind of learn different things. So there's this structure in the top left of the matrix that's very well revealed by the simple contagion. The complex contagion doesn't see it. But there's these kind of interesting bands on the side. The simple contagion doesn't see them at all, and the complex contagion sees it. So basically, like if you treat this as an inference problem of like sending a contagion to a network, they will tell you different things about it. So, and both of them will disagree in a sense. We also tested like kind of how long do you need to observe the system to say anything about it. So there's this measure in machine learning called the OROC, the area under the receiver operative character curve. And it basically tells you like how much do you learn about your system. So it goes between 0.5 and 1. 0.5 is like random. 1 is very good. And so you can see that the simple contagion kind of takes a long time to be learned, but tops out at the top. So if you observe a system for a very long time with a simple contagion, you'll be able to infer it. Whereas a complex contagion, you kind of learn faster, but then at some point you top out. You can't learn everything. Yes? What? Yeah. Yeah, it's the same graph. We matched the contagion so that they would create as many transitions and everything. So I skipped over, yeah, lots of details. But basically, we have a similar amount of data for the two. It's the same network, and then the only thing that changes is the type of contagion. Another thing that you can do is kind of vary the rules and understand how much they impact the results. So here we have this kind of complexity index, so we're basically interpolating between simple contagions and complex continuously. So on this side it's simple, on this side it's complex, and here we're changing the infectivity. So there's kind of a sweet spot where you want your contagion to be, this is for a fixed network, you want your contagion to be kind of complex but not too much, and also kind of not too infectious, right? So if it's not infectious enough, there's nothing that happens, so you can't tell what the network is. If it's too infectious, everything is always kind of infected, so you learn nothing. You don't have any transitions. So you want to be like close to the critical point, basically, to learn anything. And complexity sounds like it helps, actually. Okay, I think I'm closing on time, so maybe I'm going to show one last set of results before finishing. So this is another results where what we did, we generated a bunch of networks. So we looked at the impact of the structure here. And so here's an Erdős-Renyi network, right? So the density is fixed, and then otherwise everything is random. And we can vary the density, so those are very sparse networks, those are fully dense. And then what we compared is like how good do we do with complex versus simple. And so when it's red, complex is better, and when it's blue, simple is better. And here these kind of little lines of the white lines through the figures are lines where R naught is fixed, so the reproduction number is fixed. So that's basically essentially where the density of infectious contact is maintained. And so here you can see that like kind of on one side of the line, if you're below the critical threshold, simple is better. If you're above, complex is better. And that turns out to be kind of true across like network structures. So you can have power laws, clustered networks, and that's always the same picture that emerges. So it sounds like complex reveals more about networks right above the critical threshold. And below, you're better off sending a simple contagion. Probably in the real world, we're something complex-ish because there's a lot of mechanisms that generate these. And so we probably want, if we want to be able to infer a network, it's probably in the case where things are bad and things spread a lot. Okay, so those are the takeaways for this part. We're kind of able to reconstruct the networks and the rules. I didn't show you the rules, but you will have to take my word for it that you can also get what's the function in this case as a side effect in a way. and simple and complex kind of give you different cases where the quality of the reconstruction really depends on the kind of spread dynamics you have. And it's mostly in dense networks or a little bit saturated dynamics where complex is better. Okay, so with this, I want to thank the team. So Sam Scarpino, Laurent Hébert-Dufresne, Will, and Nicholas, also our founders. I want to also say that Nicholas is transitioning to University of Vermont, of Virginia, so the different UV in the US, and he's starting his lab. So if you think this kind of work is cool, he's hiring, so you should reach out to him. Thank you.
Thank you, Jean-Gabriel. So we have time for questions.
Well, thank you for the nice talk.
Thanks.
And, well, question is, I understand that fitting this beta of I has this very clear underlying hypothesis that it is a function of I, right? So I was wondering if you know of any way to test this hypothesis against something that, oh, it depends on I, but also on the time.
Yeah, I've not thought about, I don't know of anyone that does it. I know some models, so there's old papers, that was pre-COVID, so I would have to catch up to like all the literature that has happened since. But some people were doing just a function of time. And it's cited in the paper. We were doing a function of I, so I think the best way to do that would be to set up a function of times ni, where basically the residuals are time. And then you want to kind of regularize it in a way that the models can tell you, do you need time or do you not need time?
Yeah, yeah, that sounds complicated, but also interesting. No, I'm curious.
But like, you know, as physicists, right, like it feels like the time is kind of a driving force. It's like, it can explain too much. So it's more parsimonious to explain in terms of like I over T, so I prefer it as a model. It's like,
yeah, for sure.
right?
I agree. I agree. From the modeling perspective, if it's just a function of I, you can do a lot of like dynamical systems analysis. And one more question, please. And what about like, so that was, you said it was an SIS, right?
Yeah.
Okay, so.
Well, so no, the beta, so I kind of mixed both, but the beta I was a SIR. But then the simple case, the proof I did was SIS, and because it's just simpler. So, but there's a SIR version of it.
All right. Oh, that was my question. Thank you for answering. That was like if you add immunity or something like with Wayne immunity. That's
Yeah, I don't know if you had like a fort compartment if that still works, but like SIR, SIS, the two proofs are in the paper.
Okay. Thank you very much.
Thank you, Paul.
Good. More questions?
Hello. My question is related to, so I guess that when you try to reconstruct the network from the time series, you aim to achieve a certain degree of accuracy in your prediction. So a priori, how much accuracy would you say you need to say that your method is working? Because I guess it depends on what you want to answer, right?
Yeah, so it depends basically on the rules, right? So I think that's the figure that speaks the most to it. Yeah. It'll depend on kind of what you use. OROC is like a good one. It's rare that you can reconstruct everything. So here I skipped a bunch of details, but we were using 1,000 measurements. And so at like the 1,000 measurement step, you can basically say everything if you're close to critical. So that's what I would call like a good reconstruction. But yeah, there's cases where it's an impossible problem, right? If you don't see any transition, then it's kind of hopeless, and you would need different data sources. So that's when, like, if you're kind of a problem-driven over method-driven, you go for like surveys or something like this instead.
Okay, and then the other question is, how long should the time series be in order for you to reproduce this? I mean, what is the minimum amount of information you need?
And this net, so we don't have very like formal results so far. We just got started on this, but numerically, like in this case, there's like maybe 50 nodes, and we need like 10 to the 3 time steps.
Yeah, but this is in relation to the network size. I mean
right, exactly.
This is 10 to the 3, but this is network of what size?
So 30, 50-ish nodes, so maybe, like 100, 200 edges. So it seems to be like like my guess it would be like a certain multiple of the number of edges, right? So that's the important quantity here, but I don't have any formal bounds for you. This looks like it's 10 times maybe the number of edges.
And last one, have you tried any other dynamics?
No. Complex contagion is like, we started with higher order basically, and then ended up doing complex contagion because they're kind of the original higher order, right? Like you have the neighborhood, so maybe it depends on how you blend things. But I think it would be interesting on like hypergraphs, for example. That's a direction we're trying to go. Yes.
So thank you for your presentation. It's just a quick question, really. Did you compare your new method to things like visibility graphs or like causal inference and things like that? Do you have
No,
results on that?
we did not. So I'd be curious to see what it does. We did compare it with like random baselines, which is like the dumb guess you can do. It's actually pretty hard to do better than just, if an oracle tells you the density of a graph, like you're already quite a bit of the ways there. So I'd be interesting. So you said causal discovery as a method?
Yeah, there are some methods that make reconstructions of networks based on like causal inference. As I said, there's one that I use that's called PCM-SCI. Which is the most known one that I actually know about for reconstruction networks. So I was just willing to know the difference between your method and theirs.
Yeah, we haven't done this yet. There's this nice package in Python called netrd out of Northeastern University, and they have like 30 methods in there. So I'd be like really, we need to still feed this through, I think, netrd to see the baselines. But I will say this is Bayes optimal, but I mean, that's kind of a cheap thing to say, but when you do Bayesian inference, you're Bayes optimal, therefore, it's probably hard to outdo. It's very costly, but it's probably the best, just on generic kind of Bayesian reconstruction theorem, I'd say.
Okay, thank you.
Okay, do we have time? We have time for one more short question. Anyone? No? No?
Okay.
Okay, good.
Thank you so
Let's
much.
thank Jean-Gabriel again.